bonded, and measure half the distance between them. All right. When you go, and then the patterns, the trends, these are what we need to like memorize. Okay, we need to think through the explanations for why these are that way, and then memorize the trends, okay, and be able to think through the trends as well. Whenever we go down a group on the periodic table, we talk about a group that's a vertical column on the periodic table. Whenever we go down the group, the principal quantum number, that n, is going to increase by 1 every time we go down. And that means we're going to get electrons that have more energy, and more energy means they're further away from the nucleus. So whenever we go down a group, the radius of those atoms is going to increase. The size of the atom is going to increase. Electrons have enough energy to get further away from the nucleus, and they're going to occupy a larger space. So there's a couple of slides to help us think through why that is the case.
Sorry, so I saw there's 4, so the last slide you had?
Properties and
Yeah, so not those 3, but the next slide. So those 3. So are they talking about the one, so like the same thing, or just, so the 3, so all about the energy? It's all about, so more, so, and then, but what's the group talking about? It's just the line of periodic table?
A group is a vertical column on the periodic table.
Vertical column.
So as we go down a group, as we get to a row on the periodic table that's lower,
Okay.
The atoms will be bigger in size. All right, so just a couple slides for why. We'll just briefly talk about that. When you go down a group, you're going to have more effective nuclear charge. That nuclear charge is from the protons in the nucleus, but it actually kind of gets hidden a little bit by the electrons that are closer to the nucleus than the outer electrons. We call that shielding. We say that that an electron in the outer part of the atom has the effective nuclear charge is shielded by the electrons that are closer to the nucleus. And because of that, the outer electrons don't feel quite as strong of a pull towards the nucleus, and they're able to get further away from that nucleus. So those core electrons, the ones that are closer to the nucleus, the ones that are lower energy levels, they shield the charge pretty effectively. They kind of hide the charge from the outer electrons, and allow the outer electrons to be further away from the nucleus. However, for the electrons that are in the same energy level, perhaps a diagram might be beneficial. If we think about the positively charged nucleus and the electrons in their energy levels. Negatively charged electrons. If you have a particular electron, like this one right here, it's going to be attracted towards the nucleus, but the nucleus again is partially hidden or shielded by the electrons that are sort of in the way, that are closer to the nucleus than that electron. However, if you have other electrons in the same energy level, they really don't do a very effective job at hiding the nucleus. They're in the same energy level. We can almost think of them kind of going back to our Bohr model or planetary model. If we add an electron, this guy is not going to do a very effective job at hiding the nucleus from this electron. However, when we go across the periodic table, what that means is we are increasing the atomic number. If we, for example, going across the periodic table in row 4, every time we go to elements that are further to the right on the periodic table, the atomic number increases. It means we have an extra proton, which means we have more positive charge in the nucleus. Feels strange having cameras pointed at me. we have more positive charge in the nucleus, that means the electrons are actually going to be attracted more strongly towards the nucleus. And as we go across the periodic table from left to right, these guys will actually make the atom smaller. The radius decreases as we go across the periodic table. So this diagram kind of shows this.
Okay, that's enough.
Let's look at this column on the periodic table, group 1. As we go down, we're adding an energy level. We're giving the electrons enough energy that they can be further away from the nucleus. Our atom's radius, our atom's size increases. However, as we go across the periodic table from left to right, we're adding more positive charge in the nucleus, attracting the electrons more strongly towards that nucleus. As a general trend, the atoms get smaller as you go from left to right. If you graph this as you increase the atomic number, then you get sort of a pattern. You get a peak, and then a trough, and then a peak, and then a trough, and then a peak, and then a trough. And it's that repeated pattern of peaks and then troughs is what we call a periodic nature of this radius. Notice that the peaks occur for elements that are on the left side of the periodic table: lithium, and then sodium, and then potassium. And then rubidium elements that are on the left side of the periodic table. As you increase the atomic number after that peak, you're going to add some extra charge that's going to pull that electron back more closely toward the nucleus, make that atom a bit smaller. If we look at the radius of an ion, how do you get an ion? You add or take away an electron. What happens if you add an electron? What kind of an ion do you get? A negative. What do we call that negative ion? An anion. Okay. If we add an extra electron, we get an anion. Extra electron means that there's more electrons repelling each other without any extra positive charge pulling them back towards the nucleus. That makes the makes the ion bigger. Conversely, if we take away an electron, we get a cation, a positively charged ion. If we have fewer electrons, then they'll take up less space. They will repel each other less. So our cations are always smaller than the atom from which it's derived, we call it parent atom, versus the anion. It's always going to be larger than the atom from which it's derived. Putting in an extra electron, that electron will repel all the other electrons, try and get a little bit further away.
Miss Allen. So I didn't understand. So what is saying by like the ion from which it's derived? Is it saying this original atom or like?
So remember, we had CS just a bit ago, and we had 55 and 53 or whatever. Our protons, neutrons, and electrons. Our protons were 55, our neutrons were 78, and our electrons, well, if the charge is 0, if it's an atom, that implies that the charge is 0, which means that the number of positively charged protons must equal the number of negatively charged electrons.
Okay.
If we turn this into an ion, like for example CS+, how do we do that? We do that by removing an electron. So when we talk about the atom from which it's derived, it would be the element with neutral charge of the same type that you're talking about.
Okay.
The cesium atom with neutral charge. Sir?
Is there a difference between valence electrons and core electrons?
Yeah, so valence electrons are ones in the outermost shell of the show. And here's just a pictorial representation of exactly the same thing. Aluminum, the ion, positively charged ion, the cation, is much smaller than the aluminum atom. Whereas if you have a negatively charged ion, like sulfur, it's quite a bit larger than the neutrally charged sulfur atom. Okay? And the numbers they represent the radius, the atomic radius. Speaking of atoms and ions, it's actually possible to have an atom of one type have the same electron configuration as the electron of another type. For example, you could have a nitrogen atom. How many electrons does a nitrogen atom have? Nitrogen atom has 7. If we turn that nitrogen atom into a -3 ion, how many electrons would it have at that point?
10.
So it would have 10. We get a -3 charge by adding 3 more electrons. What about an oxygen atom? Oxygen atom has how many electrons? 8. If we add 2 more to make it a -2 charge, it would have 10. A nitrogen ion in N3- and an oxygen ion O2- have electron configuration that's exactly the same. Same thing as a fluorine atom, a fluorine ion with -1 charge, a neon atom, a sodium ion with a positive charge. How many electrons has a normal sodium atom? Normally
11.
sodium has 11. To make a positive ion, we have to take away 1 and give it 10 electrons. They all have the same electron configuration because they have the same number of electrons. And for the most part, that's going to determine the size of those species. All of these ions and atom or neon have about the same size. But the one with more protons would be a little bit smaller because it's going to attract those ions more. Additionally, these are going to have about, in many cases, some other similar properties. If they are isoelectric, these elements, atoms and ions in each row are going to have some similar properties. All right, the second property that we want to pay attention to, how it changes in different parts of the periodic table. Okay? And that second property is ionization energy. Ionization energy. That's the amount of energy required to remove an electron. We most often talk about the first ionization energy, which is the energy required to move the electron that is most loosely bound to the atom. Amount of energy required to take an atom and turn it into a positively charged ion with the electrons separated. If we had something that could be represented by this diagram, it would be removing the electron that is held least strongly to the nucleus. That's in general going to be the one that is the highest energy level, the one that is furthest away from the nucleus. Okay? In principle, it's possible in most cases to remove lots of electrons to get not just a first ionization energy, removing the one that's least tightly held, but you could also remove the next more tightly held one, and the next one, and the next one. So you could have a second ionization energy, a third ionization energy, and so on. And that's the energy just to remove these electrons. Yes, ma'am?
Would the first ionization energy be the same for both of those because they're on the same shell?
So not quite. So this one is going to be attracted to the nucleus, and it's going to be repelled by all of the electrons that are nearby. If you remove this guy, then removing this electron would actually be a little bit more difficult because you're not gonna be repelled by that electron because it's not present anymore.
And would it also possibly depend on the position that they're in, like if they have a shape and they're further away?
So it would depend on the sublevel, the shape of the orbital. That kind of determines how far away on average they are from the nucleus. Again, we can't quite think of these as being a single dot that goes in a nice circular path. That's not quite true. However, we can kind of think of the radius of the circle that I've drawn here is kind of like the average distance they are from the nucleus for that orbital that they're in. So rather than having a single orbit like the Bohr model might have, you might actually have something like two orbits that are near each other, and this would be like the 3s, and this would be like the 3p or something like that. All right, so it always takes energy to remove those guys, so these are always endothermic processes, and there's kind of two rules of how much energy is required. First of all, when you're talking about electrons that are farther away from the nucleus, it's easier to remove them, so the ionization energy is lower when your radius is bigger. Okay? So the ionization energy, therefore, decreases when you go down a group. When the radius is bigger, the ionization energy is smaller, it decreases. And it increases when you go from left to right, across a row on the periodic table. Although there's some deviations from that pattern, and most of those come about because of which sublevel the electrons are in.
So the closer the electrons is to to the nucleus, the easier to remove it?
No, the closer the electron is, the bigger the ionization energy. The more energy you have to pay
Oh, that's what I
to
saw.
pull that electron away.
Yeah. Oh, I read that wrong. Sorry. Yeah, that's what I thought.
Alright, so we get, again, we get a pattern. Notice that instead of a peak and then a gradual decrease, we get a gradual increase and then a sharp drop off. We get an increase to a peak and then a sharp drop off. We get an increase to a peak and a sharp drop off. We get an increase to a peak and then a sharp drop off. And notice where the peaks happen. For our atomic radius, which elements were at the peaks? The ones on the left side of the periodic table. If you look this way, that side of the periodic table. Lithium, sodium, potassium, rubidium. Here for ionization energy, we get elements that are on the right side of the periodic table. The noble gases, helium and neon and argon and krypton and xenon and radon. Okay? So we get sort of the opposite pattern, and again, we get some of these smaller deviations, and again, that mostly has to do with electrons that are in different sublevels. S and D and F, they have a little bit different average distance from the nucleus. And the first ionization energy for some of these elements are listed, and notice that we get the biggest numbers towards the right, and especially towards the top right. Helium being the very biggest, and the very smallest measured value being for cesium. Francium, the elements are so rare, you get so few atoms of francium, they've never actually been able to measure that. We would predict that it would be even smaller still, because the electrons for francium are even further away from the nucleus and more easily removed. Okay? And again, notice as you go across, because there are more protons pulling that electron toward the nucleus, that energy gets a little bit bigger as you go across. Notice as you go down, the numbers get smaller because the electrons are further. And before we finish, I wanted to that, if you're talking about removing another electron from those atoms, that gets, considerably more difficult. When you have, an electron already removed from the atom, the whole thing is positively charged and the whole thing will actually trap the electron back. So these successive ionization energies increase quite a bit. So for potassium, the first one's very easy to remove, and the second one's very hard to remove. The ionization energy increases significantly. Notice for some of the elements